All right, so ready to dive into something pretty massive, a work that centuries later, we're still feeling its impact and debating it, of course. I'm talking about Newton's Principia Mathematica.
Yeah, Newton's Principia, for anyone who loves philosophy, like yourself, it's not just about the history. It's like a key that unlocks these big, enduring questions. Questions about knowledge itself, about how we do science, about the universe. I mean, it's not just physics, right? It's like philosophy of science baked right in.
Exactly.
Yeah.
And that's why we're doing this deep dive,
Yeah.
especially for you. We're going deep beyond just the basics because the Principia is more than just like physics equations. It sparked these huge philosophical discussions. Think about it. How do we explain things scientifically? What's the connection between math and reality? And how do we even begin to grasp the vastness of, well, everything? And we've got these awesome sources that help us unpack all of this.
If you look at the big picture, like intellectual history, the Principia is not some dusty relic. How we understand its meaning for philosophy, it's changed a lot over time. Like the questions change, the philosophical frameworks change, and so does our view of the Principia. And today, our main guide is the Stanford Encyclopedia of Philosophy's entry on it. It's a really respected source, very comprehensive, gives us the full picture of this work and how people have thought about it, argued about it for centuries.
Okay, so the Principia, huge deal, obviously. But our source material starts with a bold statement. It says, no other work of science has attracted more attention from philosophers. Wow. What is it about this one book that just keeps philosophers coming back?
Well, that's the million-dollar question, isn't it? Why has the Principia just captivated philosophers for so long? And as the entry points out, the answer, it's not simple. The focus, like what specifically grabbed their attention, that's shifted over the centuries, as philosophy itself has changed.
Right. It mentions that in the 20th century, it was all about Einstein and relativity. How does Newton's gravity fit with Einstein's? And what does that mean for, well, what we can even know about science? What are its limits? Deep stuff.
Exactly. And for you as a philosopher, it's fascinating because it shows that even a theory as seemingly complete as Newton's can be reevaluated, refined. It highlights how our understanding of the universe is always evolving.
Totally. Philosophers were wrestling with this idea. What does it mean for a successful theory, like Newton's, to be kind of superseded? Was he wrong? If so, what does that tell us about scientific truth? How do new theories build on old ones? These are like classic philosophical questions made super relevant by Einstein.
Absolutely. Back in the 18th century, though, it was a different set of worries altogether, wasn't it? The big sticking point was, like, how does gravity even work? How can it act across huge distances with nothing connecting the objects?
Right, like no strings attached, literally.
Right. And the dominant view at the time, especially from Descartes, was all about explaining the universe through direct contact. Like, imagine gears and levers on a cosmic scale. So Descartes had this theory of invisible vortices, matter swirling around, pushing the planets. That's what Newton was up against.
So for those philosophers, Newton's gravity, this action at a distance, it seemed impossible, like breaking the rules of how the physical world should operate.
Exactly. It sparked these intense debates about cause and effect in science. What even is a scientific explanation? Can math alone describe reality?
And boom, 19th century rolls around. Now, Newton's theory is established. It's like the scientific success story. So philosophers shift gears. Now, they're interested in how Newton achieved this. What is it about his methods, his use of math, his approach to observation that led to such a powerful theory?
Yeah, it's like they wanted to decode the recipe for scientific success, right? They saw the Principia as this blueprint, and that reflected a growing confidence in the empirical method. Like observation, experimentation, that's how we get to the truth.
Okay, but our source throws in a warning here. It says that across all these periods, the philosophical discussions suffered from, and I quote, a quite simplistic picture of the Principia itself. Ouch.
It's a needed call-out. The Principia, it's not a light read. It's dense, complex. And if you reduce it to sound bites, if you only focus on one part, you're missing its real depth, its nuances. And that's what we're trying to avoid. We want to go beyond the simple picture, explore the complexities, just like a good philosopher would savor a well-crafted argument.
So let's talk about why the Principia was such a big deal. The overview in the SAP entry gives us a few key points. First, it was absolutely crucial for physics and astronomy, right?
It was revolutionary. It changed everything. Before Newton, people thought about the heavens, the stars, as separate from Earth, following Aristotle's ideas. But the Principia said, no, it's the same force gravity that governs both the falling apple and the moon in the sky. A radical idea.
It unified those two realms. It also says that after Newton, The goal of physics became about finding these fundamental forces and expressing them as laws. He basically set the research agenda for centuries. It's like he changed the very aim of science.
Absolutely. It wasn't just about describing what we see anymore. It was about finding the underlying causes, the forces, and expressing those forces mathematically. That's what we now call fundamental physics, searching for the building blocks of the universe and the rules that govern them.
And here's what I found really interesting. The Principia led to this new idea of what exact science should be. Even tiny discrepancies between what we observe and what the theory predicts, those are seen as clues, as important. That's a huge shift in thinking.
Huge shift. It's like science went from being mainly qualitative to quantitative. Precision became super important. Even small errors, they weren't just dismissed. They might point to new physics or to refinements we need to make to the theory. That's a defining feature of modern science.
The Principia also show that sometimes a good theory can actually tell us more about complex motions than just observing them. It uses the example of the moon's orbit. That seems counterintuitive, doesn't it? Like, wouldn't looking be better than just thinking about it?
Well, it shows the power of having the right theoretical framework. Newton's gravity gave us the structure to understand what affects the moon's orbit, like Earth's gravity, the sun's gravity, how they all interplay. And that allows for a more precise description than just observing it without that theoretical understanding. The theory helps us interpret the observations.
Right. And then our source contrasts how people viewed the Principia before and after Einstein. Before Einstein, it was considered this perfect model of science, almost like Euclid's geometry. You have your axioms, your truths derived from them, and boom, there's your system.
Exactly. Like the gold standard. Human reason observation leading us to these fundamental laws of nature. It was like Newton had provided the complete picture of how the universe works, at least in its realm. Certainty.
But then Einstein comes along and, well, Newtonian physics is no longer perfect. It's still accurate, but only under certain conditions, like not at super high speeds or near crazy strong gravity. It's like the map got updated. The old map was still good for some things, but it wasn't the whole picture.
Exactly. Einstein's relativity, it showed us that Newtonian physics works really well in most everyday situations, but it breaks down in extreme cases. So what was once seen as universally true is now understood to be a great approximation, but an approximation nonetheless.
But even after Einstein, the Principia is still considered foundational. Why? If it's not perfect, why does it still hold such an important place?
For two reasons that are super relevant to philosophy. First, Einstein didn't start from scratch. He built upon Newton's work. He figured out where it worked, where it needed tweaking. Second, there's a logical link between the two. Einstein showed that under certain conditions, when things aren't too extreme, Newtonian gravity pops out of his theory.
It's like when Newton showed that Galileo's ideas about gravity were a simplified version of his own. Or like how a zoomed-out map can still show you the basic layout, even though it doesn't have all the details of a zoomed-in one.
Exactly. So even though it's not universally applicable, the Principia is still this awesome example of how science works and a crucial stepping stone to our current understanding. That's some legacy.
Okay, so right after the Principia was published, some people made wild claims about it, like Newton had solved everything. But the source points out that the more realistic view was, well, it was more about the potential, like what it could lead to. So it wasn't just instant universal praise.
Right. People recognized the power of what Newton had done, but there were still some loose ends, issues that needed to be addressed. One big one was this discrepancy with the moon's orbit, its apogee. It didn't quite fit with the idea of a pure inverse square force. It showed that the theory was super successful, but maybe not perfectly complete.
And Newton, he knew about these issues, but he didn't exactly highlight them for everyone to see. Do you think maybe he just knew they could be resolved, or maybe he recognized that his initial treatment had limitations?
I think it's a bit of both. He might have had a strong intuition that his framework was solid enough to account for those discrepancies eventually, even if he didn't have all the answers right away.
And it seems like by the mid-18th century, things had changed. Some of those loose ends were tied up. Other scientists, building on Newton's work, really made it solid. That's how we got what we now call Newtonian mechanics. It wasn't just Newton alone.
Exactly. It was a collaborative effort. Researchers like Clairaut and Euler, they used Newton's foundation. They developed new mathematical tools like calculus, and they applied them to the complexities of planetary motion. And they successfully explained those deviations from Kepler's laws. That solidified Newton's theory of gravity. It was a win for the Principia as a whole.
Now, our source also talks about how the Principia challenged that whole Cartesian view of the world, the vortex theory. Newton even changed the title to Philosophiae Naturalis Principia Mathematica, which was a direct reference to Descartes. It's like he was laying down a challenge.
He was absolutely positioning his work as the new foundation for understanding nature. He wanted to get rid of those invisible vortices that Descartes proposed. Instead, he offered a universe governed by forces acting across distances described mathematically.
Interestingly, though, that whole clockwork universe idea, that super-deterministic view, it's not in the Principia. That came later with Laplace. So Newton's work, while it did suggest a universe governed by laws, it didn't necessarily mean everything was predetermined from the start.
That's a common misconception. Newton's work definitely leaned towards a universe with laws, with predictability. But this clockwork metaphor where everything's set in stone, that was a later interpretation.
Newton was also careful with his language, like attraction, impulse. He focused more on the math, on the proportions of forces, not on their deep underlying nature, at least initially. That seems like a deliberate choice.
Right. He grounded his theory in mathematical descriptions that could be checked against observations. He was super careful, and he specifically said he was investigating the mathematical side first, the quantities of forces, their proportions, and then later he would connect those to the physical causes and explanations. But famously, he never really felt the need to provide a specific mechanism for how gravity worked.
And then there's the famous quote, "I do not feign hypotheses." He was all about deriving things from what we can observe and then generalizing from there, this idea of experimental philosophy. For philosophers, that's really interesting. What does it mean to explain something scientifically? What role do theoretical concepts play?
This is a core part of understanding Newton's scientific method. It's been debated ever since he said it. He was saying his ideas, the laws of motion, the law of gravity, they weren't just guesses about what's happening behind the scenes. They were based on observations. He argued that gravity clearly exists, it explains how things move, and that was enough. We don't need to know the why of gravity, the deepest reason, to understand it.
But that led to a big challenge in the 18th century, right? This whole idea of forces acting at a distance with no clear mechanism. For a lot of philosophers, a real explanation needed to say not just what happens, but how it happens.
Absolutely. Thinkers like Huygens and Leibniz, they really struggled with action at a distance. It was a huge point of debate around the Principia. To them, it was like a flaw in Newton's account. Beautiful math, but where's the physics? Where's the actual explanation?
Okay, so the story we usually hear, Newton just came along and explained Kepler's laws. That's way too simple, right? It sounds like astronomy back then was much messier than that.
Way messier. The typical story is super simplified. For starters, Kepler's laws, they weren't just accepted as the truth before Newton. They were more like one approach among many for calculating how planets move, and not even the most accurate one. So Newton wasn't stepping in to solve a problem that was already understood perfectly.
For philosophers, that's important because it shows that science often involves choosing between multiple theories, none of which are perfect, not just confirming one established truth.
Exactly. There were other ways to calculate orbits, and they all had about the same level of precision, which was pretty low. Newton actually knew about 7 different methods, and only 2 of them consistently used Kepler's area rule, one of his key laws.
So it wasn't even clear back then that the planets moved in perfect ellipses, like Kepler said.
Right. Kepler based that on Tycho Brahe's observations, but it wasn't proven. Some planets, like Mercury and Mars, they didn't quite follow the ellipse perfectly. They had small deviations.
So the real question wasn't why Kepler's laws worked. It was more like, which of these different methods is the best? Which is the most accurate? Which one should we use?
Exactly. They were focused on predictions, not so much the fundamental reasons for why things moved the way they did. Newton, he shifted the focus to the underlying forces.
That makes the question that Hooke and Halley asked Newton make a lot more sense. It was about the trajectory of a body under an inverse square force. They wanted to know the mathematical consequence, not for Newton to explain something they already understood.
Exactly. They were interested in the math. What kind of path would an object take if the force on it got weaker with the square of the distance? They were looking for a rigorous mathematical derivation, and Newton, well, he delivered.
And his answer was the ellipse, or a parabola or hyperbola, depending on how fast the object is moving. That was huge, connecting a force law to the shape of orbits.
Massive. He took that concept of centripetal force, which was only really understood for circular motion, and generalized it. And he showed that any centripetal force, it leads to an object sweeping out equal areas in equal times. That was the key. It let him connect that inverse square force to those elliptical orbits and show that Kepler's area law was a consequence of that kind of force.
So in his early work, Demotu, he already had some of these key ideas.
He did, but then he started revising it, and he added these new sections. That's where we find the famous Copernican scholium. That's where things get really interesting.
Our source breaks down that Copernican scholium into 3 parts. The first one talks about the heavens, the planets, being at rest or moving uniformly. And it says the center of gravity of the whole system. That's the key reference point. This seems to support the Copernican view that the planets revolve around the sun.
It does. And it's not just about observation anymore. It's a dynamic justification. Newton realized that if you consider the center of gravity and you recognize that the forces are directed towards that point, well, that fits with the Copernican idea of the planets orbiting the sun.
The second part of the scholium gets even more complex. It says that the sun isn't exactly at the center of gravity. So the planets don't move in perfect ellipses, and their orbits never repeat exactly. It's like a complicated dance, right?
Yeah.
With all these planets pulling on each other.
Right, and this was a big realization. It showed that Kepler's laws, they were just an approximation. The real motions were way more intricate. And Newton even suggested that it might be beyond us to calculate those motions perfectly. We need approximations.
And the third part of the scholium ties it all together. It basically says, look, Keplerian motion is just an approximation. So be careful about using it as evidence. It's like a warning against oversimplification.
It is, because if the true motions are so complex, it explains why those different methods for calculating orbits, they all had about the same accuracy, even though they were based on different ideas. And it means that the differences between those methods, well, they couldn't be easily dismissed just because they didn't perfectly match Kepler's laws.
So the Principia, it grew so much bigger than Demotu because Newton wanted to find answers that were truly accurate despite all this complexity.
Yeah.
He wasn't satisfied with just approximations.
Exactly. He wanted to get to the truth, even if it was messy. And the Copernican scholium, that's where he lays out his concerns. How do we get to the truth when the evidence itself is complex and maybe even misleading? It's a deep philosophical question.
Okay, let's talk about the structure of the Principia. It's got 3 books, right? Each with a different focus.
Right. Book 1, that's where he sets up the math. The theory of motion under centripetal forces. It's the foundation. And for a philosopher, it shows how powerful math can be. You can describe physical things even without knowing all the details, all the causes.
Then in book 2, he tackles motion in resisting media. That's where he refutes that Cartesian vortex theory, head-to-head with a competing worldview.
It is. He goes deep into how things move when there's resistance, like when they're moving through a fluid. And he uses that to argue against the idea of those vortices carrying the planets.
In book 3, that's where he applies all that math to the real world, to the system of the world, as he calls it. That's where he derives the law of gravity and uses it to explain how the planets move, the tides, the comets, everything.
Yeah, book 3 is where it all comes together. The math from the first 2 books meets the universe. It's the culmination of his project, showing just how powerful his theory is.
Now, the Principia starts with a section called definitions. Our source says that philosophers have had a lot to say about it. It seems like it's more than just defining terms. It's about how we understand those concepts.
Exactly. It's where he defines key terms like mass, inertia, and centripetal force. But he's not just saying, here's what these words mean. He's talking about how you measure these things. How do we actually get a handle on them in the real world?
So it's not a philosophical deep dive into the essence of mass or inertia. It's more like a practical guide. Here's how we quantify these things. Here's how we relate them mathematically.
Right. He even uses the word quantity in a specific way, like Aristotle did, not as some individual thing, but as something that has a magnitude and a direction. He's emphasizing the relationships between these quantities, how they interact.
It's operational. It's all about what we can observe and measure.
Exactly. And he has this key idea, no quantity without definite proportions. What he means is, to understand these concepts, to make them scientifically useful, we need to be able to measure them precisely. That's how we figure out the exact relationships between them.
After the definitions, we have that famous scholium on space, time, and motion. And our source says that people often misunderstand this because they don't get Newton's main point, the difference between absolute and relative motion. And that distinction, well, it's pretty important for how we understand reality.
Absolutely. This is a biggie. He's saying there's absolute true mathematical motion, and then there's a relative apparent common motion. But the idea itself, true versus apparent motion, that wasn't totally new in astronomy. Think about Ptolemy, Copernicus. They were already dealing with how our viewpoint, our perspective as observers, affects how we see motion.
So Newton wasn't coming up with something completely out of the blue.
Right. He was making it more rigorous. He was trying to give us a system to figure out what's really moving and what just seems to be moving because of our perspective.
Well,
He defines relative time as any way we measure duration using motion and this idea of absolute space, like a fixed background against which everything moves. But he also says we can't directly see absolute time or location.
we can only infer those from what we can measure, from relative motions. And those measurements can be wrong, right? There are limitations. And that raises all sorts of philosophical questions about what we can actually know about the universe.
Big questions for sure. And you see that even Newton, he doesn't pretend we have perfect knowledge. He uses relative measures like the fixed stars or sidereal time. He uses them to approximate those absolute concepts. He's focused on how we can measure changes in motion, how those relate to forces, even if our measurements are always filtered through our understanding, through our theories.
And then in his laws of motion and some of the corollaries, he seems to say, look, sometimes you don't need to worry too much about the whole absolute versus relative thing.
Right. In certain situations, it doesn't matter so much. Like corollaries 5 and 6, they basically say that if you have a bunch of objects enclosed in a space, or if they're all experiencing the same acceleration, well, their relative motions stay the same, even if the whole system is moving in some absolute sense.
So for a lot of practical physics experiments, you don't need to know how fast the whole lab is moving through space.
You don't. But the question remains. If we can't actually measure absolute changes in motion, if we don't have direct access to absolute space and time, then how do we tell what's really moving? And his answer is forces impressed upon bodies.
So it's about looking for the causes of those changes in motion.
Right. He's saying that true acceleration, that means a change in true motion, it's caused by forces. So we need to figure out how to measure those forces accurately, how to separate them from apparent forces, the ones that pop up when you're in a non-inertial frame of reference.
And he has that famous bucket experiment to illustrate this, how the water in a spinning bucket, it curves inward because of the centrifugal force. You can see the effects of real rotation, even without needing to reference some absolute space.
Exactly. And that's what the whole Principia is about, isn't it? It gives us the tools to go from forces to motions and from motions to forces. And then he applies that to the universe to figure out what forces are at play and to tell the difference between real motion and just apparent motion.
It's a huge project, explaining the universe through the lens of forces and motion.
Massive project. And it shows that those definitions he gives at the beginning, they're not just abstract. They're connected to his physical theory, to how the theory explains what we see.
Of course, we have to remember that even Newton made some assumptions about space and time that later turned out to be, well, not entirely accurate. Like, he assumed space is Euclidean, three-dimensional, and that time is this thing that flows at the same rate everywhere.
And Einstein, he showed us that those assumptions, they break down in extreme situations. That even the most basic ideas about space and time, they might need to be revised as we learn more.
But empirically, when he actually did calculations, Newton used the fixed stars as a reference frame. And he concluded that, based on observations, they're basically at rest relative to the center of gravity of the solar system.
Right. So even though he had this theoretical idea of absolute space, in practice, he used what he could observe.
So let's talk about the laws of motion. Our source points out that people were already using that term laws of motion before Newton. So he wasn't working in a vacuum, right? He was building on existing ideas.
Totally. Wren, Wallace, Huygens, big names in science back then. They were already trying to figure out how motion works, especially collisions. And some of their ideas, they kind of foreshadow Newton's first law, the law of inertia.
But even then, Newton's way of putting it, it's different. A body at rest stays at rest, and a body in motion stays in motion with the same speed and in the same direction, unless acted upon by an outside force. He really emphasizes those forces impressed. That's a key shift in thinking.
It is. The idea of inertia, that objects tend to keep doing what they're doing, that was already around, but Newton explicitly links that to forces. Like, the only way to change an object's motion is to apply a force to it. He put force right at the center of dynamics.
Now, the second law, we usually see it as F, ma, force equals mass times acceleration. But that equation, it's not on the Principia at all.
Nope, it's not. People often simplify it, and they lose some of the nuance.
So what does Newton actually say?
His wording is, a change in motion is proportional to the motive force impressed and takes place along the straight line in which that force is impressed. It's more subtle, and he meant it to apply to both instantaneous forces, like a quick push, and to continuous forces, like gravity.
Hmm.
And he used proportions instead of an equal sign.
Why did he do that?
It made it more general. It avoided issues with units. It's like he was being very careful with the math, making sure it was as general as possible. Now, for philosophers of science, the key is understanding what he meant by change in motion. He wasn't necessarily talking about momentum like we think of it today, mass times velocity.
Our source actually includes this passage from Newton where he tries to rearrange the Principia, and he explains this change in motion geometrically. It's like the distance between where the object would have been if no force acted on it and where it actually ends up after the force acts.
Exactly. He uses this parallelogram rule, from geometry to show how the force kind of pushes the object off its original path. And this actually made sense back then because the math they were using, it wasn't like our modern calculus.
It was more visual, more geometric.
Totally. They didn't have a neat way to represent acceleration as its own thing. So using a length, a distance to represent that change in motion, it fit with their way of thinking.
And our source says that this way of interpreting things wouldn't have been super weird back then. It connects to how they thought about impact, collisions, and also to Huygens' work on centrifugal force.
It does. The idea was already there, that you can measure a force by how much it moves an object in a short time. Newton, he just generalized it. And importantly, he swapped out these vague ideas of bulk and weight for mass as the measure of inertia.
The third law, action-reaction. For every action, there's an equal and opposite reaction. Newton actually considered other ways of stating this, like the conservation of momentum, right? Why did he pick this particular way of phrasing it?
He did. And those other ways, like conservation of momentum, they actually follow logically from his third law. Huygens, he even derived some of these ideas from studying collisions, which were a big deal back then. But Newton chose this action-reaction principle. He made it a fundamental law.
And the others, they're just consequences.
Right. Now, our source suggests a couple of reasons why Newton might have done this. And these reasons, they're interesting for philosophers of science. First, the third law. It's about what happens between two objects directly. It's local. The other ideas, they're about the whole system. They're global.
So maybe he liked the idea of focusing on the simplest interaction.
Maybe. And the second reason, with the third law in place, now all three laws are about forces. They describe how forces act, how strong they are, what direction they're in, and how they create this equal and opposite reaction. It creates a unified system. Force is at the center.
So for Newton, a real force, it's something that obeys all three laws.
Yeah.
It's how you separate it from, like, apparent forces that might pop up because you're in a weird reference frame. He even presented his first two laws as, like, already established, confirmed by experiments. But the third law, that got extra experimental support, especially from studies of impact.
Right. He wasn't claiming to invent this whole new idea of force. He was building on what people already knew, like from studying levers and balances. He was taking that familiar idea of static force and expanding it to cover motion, to cover dynamics. And there's a connection to Huygens here, too. Huygens used that static force idea in his theory of centrifugal force.
It sounds like Newton wasn't just a lone genius working in isolation. He was part of this ongoing scientific conversation, taking ideas from others, refining them, pushing them further.
Absolutely. He was building on the work of giants, as they say. And our source outlines these three steps and how force went from being the static concept to the dynamic force that Newton used. One big step by Huygens, and then two more by Newton.
And the evidence for Newton's first two laws, it was already pretty solid by the time the Principia was published. Huygens had this sophisticated pendulum theory, and Newton, he did his own experiments, confirmed it using a conical pendulum. They both got the same value for the acceleration due to gravity.
That's important. They were using different methods, different theories, but they got the same answer. That provided strong support for Newton's ideas.
Now, a lot of people think that Newton's three laws, that's all you need to do, classical mechanics. But our source says that's not true.
Not at all. The mathematicians and physicists who really developed Newtonian mechanics after Newton, they knew that the three laws, as written, they worked best for these idealized point masses, objects that have mass but no size or internal structure. But for real objects, for rigid bodies, fluids, systems with multiple objects, you needed more.
So the three laws were just the starting point.
They were. And figuring out what those extra principles should be, that became a big debate in the 18th century.
Moving on to Book 1, Our source points out that it's not just about gravity. He develops this whole mathematical theory of motion for any kind of centripetal force. He explores forces that change with distance in all sorts of ways, not just one RRO, but one ROA and even more complicated functions. It's like he was mapping out the mathematical possibilities before even looking at the real world.
Exactly. And he explicitly says that's what math allows you to do. Explore all the options and then see which ones fit the observations. And this wasn't just an abstract exercise either. It had real implications. Like, how does gravity behave below the Earth's surface? He thought it would vary linearly with distance.
So different from how it behaves above the surface.
Different. And he also knew that forces changing as one area, they could make orbits precess, like the moon's orbit does.
So he was building a toolbox, a set of mathematical tools that could be used to analyze all sorts of forces, not just gravity.
Right. Now, book one, it does have a limitation. It focuses on forces that only depend on distance, not on angles or anything else. And our source suggests that this might have been a way to avoid the complexities of those Cartesian vortices.
Because those vortices, they would create forces that depend on the direction on the flow of the fluid, right?
Exactly. By sticking to radial forces, Newton could sidestep those complications. And later, he even admitted that gravity around a non-spherical object, well, it's not perfectly one or air either, so even his own theory, it wasn't.